Hello, and welcome to lesson 37 of this Introduction to Calculus with Wolfram U. The topic for this lesson is separable differential equations. So let's begin with a brief overview of the lesson. So the fact is that most differential equations cannot be solved easily. So for example, here's a nonlinear equation. What I mean by that is you've got a y of x the whole square over here, and desolve can solve the equation, but the solution is rather messy and involves these so-called Bessel functions which occur in the oscillations of drums and elsewhere. So, in contrast to that, there are other equations where you actually can find a simple solution. So here's an example where the solution is quite simple, and if you look over here, uh, in part that's because the differential equation itself is a bit simpler. So this is an example of a separable differential equation. And the theme of this lesson is to talk about these separable differential equations. So the question is, what is a separable differential equation? Well, a separable differential equation is an equation of the form y prime, the derivative of y, equal to some function of x times some function of y. Okay, now if you look at this, the right hand side is certainly what you would call separable. You can separate x and y. The question is, how about the left hand side? Well, recall that y prime is dy over dx. So you can think of that as a separation for y prime. So for example, here is the differential equation that we spoke about in the earlier slide, and if you want to solve it, you replace y prime by dy over dx, and then you separate your variables like over here. So you have 1 over y dy equal to x dx, like you do in algebra. Then you integrate both the sides, and then you say that this y is e raised to power c plus x squared over 2, but then that's the same as e raised to c times e raised to x squared over 2, and then that itself, the e raised to c, is another constant which you can call k. So the solution is y equal to some constant times e raised to x squared over 2. That is the general solution of the differential equation. Okay, so on to another example. Let's try and solve the differential equation y prime equal to y. So in this case, you can think of f of x as being 1 and g of y as being y. So that's the separation of the right hand side. Keep in mind that y prime is dy over dx. So you separate your variables, rearrange, and you get dy over y equal to 1 dx. Then integrate both the sides. I haven't put the constant over there, but it's certainly there in the background. So y is e raised to x plus c, where c is the constant. So you get e raised to c times e raised to x. That's k times e raised to x. And you can confirm the answer with desolve value, and you get back just the same result. Okay, so on to a slightly harder example where you have y prime equal to 3x cubed over 4y plus sine y. So in this case, f is just the numerator, and for g, you can take 1 over the denominator. So that's the differential equation. And then you separate the variables, rearrange, integrate both the sides separately, and now you see that the solution is going to be 2y squared minus cosine y equal to 3x to the power 4 over 4 plus c. And here is a plot of the solution with contour plot. Okay, so the question is, what happens when there are initial values? So let's take the equation y prime equal to x times y with the initial condition y of 0 equal to 1. So that's an initial value problem with the value of y given at 0. And the question is, can you then find a particular solution of this differential equation? So let's rearrange the equation as earlier, solve it. So you get y equal to k, where k is a constant, times e raised to x squared over 2. Now you plug in the initial values, so you get y of 0 is 1, so you get 1 equal to k times e raised to 0, so k is 1. and your solution is y equal to e raised to x squared over 2. And you can confirm that with dsolve, and also check the solution plot by doing a stream plot. Okay, so on to some applications, and we'll take two of them. The first one is for current. So here's an equation that describes a circuit in which there's some charge flowing, the resistance, a capacitance, and some voltage associated with the circuit. So that's the equation, the differential equation for the charge Q. Now, of course, if V depends on T, that's much harder. So we'll assume that V itself is a constant. So you've got constant resistance, capacitance, and voltage. And in that situation where V does not depend upon T, you can solve for Q prime, and then you see things are separable over here, so you separate the equation and get an expression for T in terms of everything else, but you want to solve for Q, so you solve for Q, and the normal way just means that you're ignoring some conditions on Q. So the solution is C times V minus e raised to that expression over there. But if you think about this, it's really e raised to minus k over c times e raised to minus t over r. That's just k times e raised to minus t over c times r. And one final point, that as the time approaches infinity, as more and more time goes by, the value of e to the minus infinity is 0, so this term drops out, and the final solution is that the charge approaches c times v as t approaches infinity. And a second example is for Newton's law of cooling. So here is the differential equation for the temperature when an object at temperature T0 initially is placed in a medium where the temperature is held constant at S. So what happens is that the rate of change of temperature is proportional to the difference between the current temperature and the temperature of the surrounding. And as time goes by, when the difference becomes small, the rate falls down as well. So you need to determine K, and we're given the initial condition that the temperature at 0 is T0. Now, of course, over here you have a separable equation, so you separate the variables and you get back an expression for T in terms of temperature, but you want to solve for temperature, so you do that and you get an answer. Now, the point is that e raised to c times k is a constant. So again, you can call that some c, and you solve for that constant. So the final solution is that the solution, the temperature at time t is minus s plus t0 times e raised to kt plus s. And you can check the answer with dsolve, and you get back the same expression. Now, the question is, how to determine k? Well, to find k, what you need is the temperature T1 at some later time tau. So suppose you know that temperature, then you plug the values into the solution and you solve for k, and that is the expression for k. So the constant k is the logarithm of s minus t1 over s minus t0 over tau. So as an application, let's say you've got a cup of boiling coffee at 100 degrees centigrade. It's boiling, and you put it in a room in which the temperature is 22 degrees centigrade. And let's say an hour later, the temperature of the coffee is 60 degrees centigrade. Then what you can do is you can model the coffee temperature by the equation over here, where I've plugged in the value of k based on the given information. So that is the starting temperature, that's the room temperature, and you want to model the coffee over a period of time. So let's see what happens to it over a period of, let's say, 10 hours. And you can see that the temperature slowly approaches the room temperature, which is 22. And in fact, you can use limit to check that the answer is actually 22 when you have let infinitely many hours pass by. So that's Newton's law, which models the cooling of objects which are placed in a room with a higher temperature than room temperature. Okay, so that brings me to the end of the lesson, and the main point is that separable equations are, in general, rather easy to solve. And the way that you solve them is to note that the right-hand side is a function of x times a function of y, and then you can replace y prime by differentials dy and dx and then solve the equation. Now, of course, you can use that to model various phenomena. So, for example, you can model the charge in a circuit by a separable differential equation, or you can model the temperature over time for a hot object using separable differential equations. So, in the next lesson, we'll talk about how we can make programs that help to solve calculus problems, including differential equations. But before that, do revise today's lesson. It's quite an important topic, separable differential equations, and I'll see you at the next lesson. Thank you very much. I'll stop over here.